Hello students, welcome to another class of physics. In this class we discuss about the average life or mean life of a radioactive sample. Okay, so the basic things about this lecture is to measure mean life, or simply we can say average life, and it is simply the symbol tau average. Okay, mean life or average life of a radioactive sample may be defined as the sum of the lives of all samples to the total number of nuclei present. Okay, again, mean life of a radioactive sample is the variation of or the ratio of sum of total lives of all the samples to the total number of nuclei present. Okay, that means sum of life. Okay, that means total life, the total time of existence of all the samples inside the nuclei to the total number of samples present inside the nuclei. Total time or sum of the life of all samples to the total number of samples. Okay, so that means we can say mean life, that is sum of all lives of all the samples to the total number of samples. Okay, sum of lives means that is the time, total time of existence of all samples to the total number of samples. Okay, so if we take the expression of the mean life, we can say simply n equals to n naught e to the power minus lambda t. From the law of radioactivity, n equals to n naught e to the power minus lambda t. Okay, suppose dn is the number of samples decay in time dt. Okay, dn is the number of sample decay in time dt, or if we differentiate, okay, so differentiate both sides, what we get, and differentiating with respect to t. Okay, so simply we say dn equals to n naught or minus lambda n naught, lambda is any constant, so minus lambda n naught e to the power minus lambda t. Okay, so suppose this is equation 1. Okay, let dn number of samples decay in time dt. Okay, that means from the initial value n0, suppose dn atoms decay in time dt. Okay, and number of sample after decay is suppose n. Okay, and the total time of decay we take for dn atom is dt. Okay, that means the lifetime of dn atom, okay, the total lifetime of dn atom will be, so again I repeat, if dn number of atoms decay in time dt, that means all the dn number of atoms remain undecayed after the time t. Okay, that means we can say the total life of dn number of atoms, okay, n equals to n naught e to the power minus lambda t. Okay, n is the number of samples remain undecayed in time, or number of samples remain present, number of sample present in time t. Okay, and from that value dn number of samples decay in time dt. Okay, that means here we can take small example n0 at t equal to 0. Okay, and number of samples n equal to t. Okay, from this value, that is the time t. Okay, and reduce will be after disintegration, left sample will be n. Okay, and the time for the n atom, or the time to decay all the atom is t. Okay, and from the n atom there will be dn number of atoms decay in time dt. Okay, that means we can say the lifetime of dn number of atoms before decay is t. Okay, if dn has a number of value, like suppose dn we can say 5 or 10, so this total number lifetime, suppose there are 1000 number of molecules or 1000 number of samples inside the radioactive element. Okay, and from that 1000 number the sample decay will be 100. Okay, the remaining will be 900, that will be n. Okay, and to decay the 100 number of samples, the time to decay this 100 number of samples will be suppose 1 minute. Okay, or simply take 2 minutes. Okay, 100 molecules or 100 samples decay in 2 minutes. Okay, and after that remain will be 900. From 1000 atoms or samples decayed will be 100 in time 2 minutes. Okay, and the remaining will be 900. Okay, and to reduce from 1000 to 900 the time takes place, that is 2 minutes. Okay, and after that in 1 second number of sample decay, suppose 10. Okay, that means we have to measure the lifetime of this 10 atom. Okay, before decay. Okay, before decay the total 10 atoms exist for the 2 minutes. Okay, that means these 10 sample present inside the nuclei within up to 2 minutes. Okay, so if we measure 10 into 2, total time of this 10 sample, that is 10 into 2, that is 20 minutes. Total time of, or the total lifetime of all sample, total lifetime, each sample exists for 2 minutes. So there are 10 number of samples, so 10 number of samples, total lifetime will be 20. Okay, so this dn number of atoms decay in time dt. Okay, and the total lifetime of this dn number of atoms before decay will be total lifetime of dn number of atoms will be tdn. That means they exist inside the nucleus up to time t, and as there are dn number of atoms, the total lifetime will be tdn as we multiply 2 with 10. Okay, and when we measure the average life, okay, so that means we can take so if there are n0 number of samples at t equals to 0, okay, and it is reduced n0 to 0. Okay, and the time for reduction, that will be infinity. Okay, that means we can say n equals to 0 when t equals to infinity, and n equals to n0, that means the total sample at t equals to 0. Okay, so the total lifetime, the total life of all samples before decay will be total life of all samples will be integration 0 to n0, okay, t dn, okay. And as we denote in equation 1, dn equals to minus lambda n0 e to the power minus lambda t dt. So, I forget to write dt in equation 1, okay. So, dn equals to minus lambda n0 e to the power minus lambda t dt. So, if we replace the integration from the dn value changes to time dt, okay. And as we say, n equals to n0 when t equals to 0 and n equals to 0 when t equals to infinity. At infinity time, the total samples reduce to 0, okay. So, if we change the integration here, that will be 0, n equals to, that is n equals to 0 and here n equals to n0. So, n equals to 0, that means we can say t, replace the value of dn, that is minus lambda n0 e to the power minus lambda t dt, okay. So, replace this value, and when n equals to 0, the time will be infinity. So, that will be infinity, and n equals to n0, the time will be 0, okay. And there is a negative sign. Negative sign means we can say we can change the order of the integration. So, that will be integration 0 to infinity, okay. There is a negative sign, so we can change the order, okay. Lower limit will be upper, upper limit will be lower. So, integration 0 to infinity lambda n0 t e to the power minus lambda t dt, okay. So, integration, take the constant outsides, lambda n0, integration 0 to infinity t e to the power minus lambda t dt, okay. So, we can integrate this by parts method, okay. So, that equals to lambda n0 into t e to the power minus lambda t. So, that is by lambda. So, first integrate this thing, okay. You can simply use UV rule of the parts method, okay. Limit 0 to infinity, then derivative of this one, integration of this one with the total integration, that means derivative of t, that will be 1, okay. So, 1 into integration of this part minus lambda t by lambda whole integration 0 to infinity dt, okay. And when we replace the value e to the power minus infinity, that is 0, and when we replace the upper limit, that will be here the term t, so that will also be 0, okay. So, there is a negative sign, minus lambda n0 integration 0 to infinity. So, this term will be 0, integration 0 to infinity e to the power minus lambda t. So, we can replace here negative, negative, that is plus, okay. Remove the negative sign, divided by lambda into dt, okay. So, that will be lambda, lambda, that is constant term, cancel, n0 into, okay, integration 0 to infinity e to the power minus lambda t dt, okay. So, e to the power minus lambda t, that is n0 e to the power minus lambda t divided by minus lambda, that is integration 0 to infinity, okay. And if we replace the value e to the power minus, upper limit should be first, okay, e to the power minus infinity, that is 0, and if we replace 0, e to the power 0, that is 1, and lower limit, that is the negative sign, that negative and negative, that will be positive, okay. So, what is the remaining value? So, total life of all sample equals to n0 into 0 minus of 1 by lambda, minus of minus 1 by lambda, simply I write here 0 plus 1 by lambda, okay. So, that implies 2, or simply that is n0 by lambda, okay. So that is the total life of all samples. And from the definition of average life, what we get? Tau average, that is total life of all sample before decay divided by total number of samples. Okay. So that will be total life, that is n0 by lambda, and the total number of samples we take, that is n0. So tau average equals to, if we cancel, that is 1 by lambda. Okay. That means the average life or mean life of a radioactive sample is equal to reciprocal of decay constant. Okay. So that means we can say mean life is equal to reciprocal of decay constant. Reciprocal of decay constant. Okay. Now from this we can relate half life, decay constant and mean life. Okay. So relation between lambda, T half and tau average. Okay. So what do we find? So relation between lambda, half life, that is T half, and tau average. Okay. From the expression of half life, what we find? T half equals to 0.693 divided by lambda, and tau average equals to 1 by lambda. Okay. So that implies to, if we relate this term, that is T half equals to tau average into 0.693. Okay. Or simply we can say half life equal to 0.693 times tau average. So that is the basic relation between, so you may use this relation, or simply tau average half life equal to 0.693 into mean life. Half life equal to 0.693 into mean life. Okay. So this is all about mean life. Okay. Mean life is the variation of total life of all samples to the total number of samples present in a radioactive nuclei. Okay. Understand? Thank you.